characteristics of cubic cells. So there are total in five. First is the volume of unit cell, second is the number of atoms per unit cell, and third is the coordination number, fourth is the atomic radius, and fifth is the atomic packing factor. So these are some characteristics of the cubic cells. Firstly, we will discuss about the volume of unit cell. So you can see in a figure, there is a unit cell, and for the cubic systems, we have A equal to B, B equal to C. So what will be the volume of this unit cell? So it would be A cube. Okay, so this is the volume of unit cell, and how we are calculating the number of atoms per unit cell. So the number of atoms per unit cells, they are equal to it is the sum of three terms. First is the number of atoms that are present inside the cell, and here you can see this is the number of atoms that are present inside the cell, and this is the number of atoms that are present at the faces of unit cell, and these are the number of atoms that are present at the corners of the unit cells. So how using this equation you can calculate the number of atoms per unit that cell. So for FCC we know that no atom is present inside the cell, so here it is 0, and no atom is present at the faces, so it is 0 here, and after that we know that only atoms are present at the corners, so there are 8 atoms. So in total there are how many number of atoms? So there is only one number of atom is there per unit cell for SCC case. And now what about BCC case? We can see here one atom is present at the center of the body and no atom is present at the faces. So, and 8 number of atoms that are present at the corners of the unit cell. So it is giving a 1/8 contribution to it. So in total we get n equal to 2 for BCC system. Okay, so now what about Fcc crystal structure? We know that no atom is present at the inside the unit cell, or 6 atoms are present at the phases, because there are 6 phases. So 6 atoms are present at the center of phase, and it is giving half contribution to it, and 8 atoms that are present at the corners, so it is 8/8. So in total we get 4. So that means 4 atoms are present in the unit cell for Fcc crystal structure. So now we talk about coordination number. So what is coordination number? Coordination number, it is defined as the number of equidistant nearest neighbors that an atom has in the given structure. So now we have here the two terms, equidistance and nearest. So means we are talking about the atoms, those are equal distance apart from each other, and those are nearest to each other, or you can say those are closest to each other. So it is defined as the number of equidistant nearest neighbors that an atom has in the given structure. So when we firstly talk about this simple cubic crystal, so this is the figure of simple cubic crystal. This is a simple cubic crystal structure. So you can see here we have drawn 8 unit cells. So you can see this is first unit cell, and this is the second unit cell, third and fourth. So in total there are 4 unit cells at the bottom and 4 unit cells at the top. So this is the simple cubic crystal structure. So when we talk about coordination number, what is this coordination number? For this, if we consider this atom which is present at the present in the crystal structure, if we talk about this atom, so how many number of equidistant nearest neighbors to this atom? So you can see here in the unit cell, if you're talking about cubic cell, So this distance is A, and this distance is also A, this distance is also A. All A, B, C are equal for the cubic crystal. And if we talk about this particular that I have circled here, so if we talk about this circle, how many number of atom, those are equidistant from this atom. So see, you can see here, if we talk about this atom, so this atom, okay, yes, there are 6. So in total there are 6. So these are the atoms that I am circling here. So these are the equidistant neighbors, and those are closest to this particular atom. And why we are not talking about this atom? Why we are not talking about? Because this is not at the equal distance. And in this way you can see, if we talk about this particular atom, and if we see this plane as a crystal plane, so how many number of atoms, those are equidistant from this atom? So there are four atoms. This atom, 1, 2, and 3, 4. So if we talk about this particular crystal plane, and so there are 4 atoms, those are equidistant and nearest to this atom. And when we talk about this crystal plane, so how many number of atoms that is equidistant from this? Only this one atom is there. And if we talk about above plane, so 1 is there. Okay, so in case for FCC, you can see one atom that is below to that crystal plane, and 4 atoms within its plane, and 1 atom above its plane. So in total, coordination number is 6 for this simple cubic crystal. And now what about the BCC structure then? So we know that in case of BCC structure, we have atom at the center of the body. So how many number of atoms that are equidistant from this atom? Yes, 8, it is written here. So if we talk about in terms of planes, we can see, if we taking this as a crystal plane, so we can see four atoms that are below this crystal plane, and 4 atoms those are above this plane, and 0 atom which is equidistant from this atom within its plane. So in total for the BCC structure there are 8 atoms. So this is the coordination number for BCC. So in the similar case, we can find out for the FCC structure. So in case of FCC structure, we know that atoms are present at the center of the phases. So if we talk about this crystal plane, and if we talk about this crystal plane, and we are finding the coordination number for this particular atom. So 4 atoms, those are present in this plane. 4 atoms are present within this plane, and if we talk about this plane, so 4 are above, 4 atoms, those are left to that plane, and 4 are within this plane, and 4 to the right of the plane. So in total there are 12 atoms which are equidistant and nearest to that particular atom. So okay, so for the FCC case, we have 12 is the coordination number. So now we talk about the atomic radius. So what is the atomic radius? To find out the atomic radius, here we are assuming that these atoms are spheres. So these atoms are in the shape of spheres, and in case of this simple cubic crystal structure, this is if you are seeing this figure, so in the simple cubic crystal structure, and we have giving the naming A, B, C, D, E, F, G, H. So here we are talking about the corners A and H, where the atoms are present at the corners, and these atoms are touching to each other. So in a cubic crystal, we assume the atoms are like spheres and they just touch each other. And if we talk about the only this front face, you can you can see this figure like this figure. Okay, so all the atoms are touching to each other, and if a atom is like a sphere with the radius of r here, so if it is r radius for this particular atom and r is for this particular atom, so this what is this cubic edge? We know that if we are having a cube, so cube with the cube edge a, so what then a will be equal to 2r, where r is the atomic radius. Okay, so for SCC structure, we see a is equal to 2r, and where a is the cube edge and r is the atomic radius. So what is now the atomic radius? Atomic radius in terms of the cube edge is equal to r is equal to a by 2 for simple cubic crystal structure. So now here it is atomic radius for BCC structure. So in case of BCC structure, you can see that one atom is present at the center. So one atom is present at the center, it is giving whole its contribution to this particular unit cell, and the atom those are present at the corners, only 1/8 is contributed to this unit cell. So but the radius of this atom those are present at the corners having this r radius, and for this particular atom which is present at the center, we are having 2r for this diameter of this atom, and r for this particular atom that is present at the corners. So in this case, you can also see the cube edge having the values a in x, y, and z direction. So in the previous one, we have seen that these atoms are equidistant along the cube edge. But in this case, we are talking about the atoms, those are present diagonally in this unit cell. So this is not equal to A. So how you will calculate this particular value? So for that, you have to firstly find out the value of this SV. So how you will calculate this SV? You can use this Pythagoras theorem. You know that in cubic cell the angle is 90 degree. So you just calculate this value of hypotenuse from using the Pythagoras theorem, and using the values of A and B for perpendicular and base, you can calculate this particular value of this diagonal along the phase. And now how you will calculate this? You can calculate the value of this diagonal when you are considering PSV as a this triangle, and we can get the value of then PV from the Pythagoras theorem. So we will calculate it in the coming slides. So now we talk about the atomic packing factor. So now what is this atomic packing factor? This indicates that how closely atoms are packed in the unit cell. How closely they are packed, because we know that in the case of simple cubic crystal structure, atoms are present only at the corners. So some part is empty in the unit cell. So in using this vector, we can know how much they are closely atoms they are packed. So this is a atomic packing factor. So it is defined as a ratio between volume of the atoms in the unit cell upon the total unit volume. So how you calculate the volume of atoms? How we will calculate the volume of atoms? We can calculate the volume of atoms by multiplying number of atoms to the volume of one atom. So we have to calculate volume of one atom, then we will multiply with the number of atoms. So we know that for a simple cubic crystal, there is only one atom. So we just calculate the volume of one atom and multiply by 1, it will give the volume of atoms in the simple cubic crystal. So when we calculate the volume of one atom, so we will multiply it by 2. So in the FCC case, we will multiply it by 4. So in that way, we get the volume of atoms in the unit cell, and we know if we talk about a cubic crystal, volume of the unit cell is A cube, but the volume occupied by the atoms is less than A cube. So we will calculate it how much the volume they are occupying. So depending upon that, we are taking the fraction of that, and that fraction is known as atomic packing factor. So here is the atomic packing factor for simple cubic. So here you can see this is the figure of simple cubic unit cell, and these are the atoms A and H present at the corners. And in the previous we have also seen that this distance between if we are talking about this point and this point as a corner, so R is the radius for this particular atom, and R is radius for this particular atom, which is contributing to this unit cell. So depending upon that, A is equal to 2R for simple cubic crystal structure, and the number of spheres and the number of atoms, we know that there are 1. So the volume of sphere, we know that how we can calculate it. Volume of the sphere we can calculate by 4 by 3 pi r cube, and we now know that what is R here, and we can find the value then. So after that, fraction of the space occupied we get by this ratio. We finding the volume of atoms divided by the total volume. So we get the this fraction by 52.4% for the simple cubic crystal structure. So now here is the atomic packing factor for BCC. So in case of BCC, we know that this atom is present at the center of body, and two atoms we are considering for the corner atoms, and we have to calculate. Firstly, we will have to calculate this diagonal, which is diagonal of the phase. This is the bottom phase. So we will calculate this phase. So how we will calculate it? We can see here in a triangle EFD. So we are talking about EFD. So this is a triangle, and how we will calculate it? Using the Pythagoras theorem, we can see this value of B comes out to be A square plus B square equal to 2A square. So the value of B is square root 2A. So the value of this B is square root 2A. And now if we want to find out this value, we have to take this triangle. So if we are taking this triangle, so now this B is the base and A is now the perpendicular. So we will calculate the hypotenuse then. So if we are talking about that this length along the diagonal is C, if we are taking this diagonal along C, so we get C square is equal to A square plus B square, and we have calculated B square, so it comes out to be C equal to square root 3A for this case. So we know that how much this square root 3A, this square root 3A is equal to 4 of R, because 2R is for central atom and 1R for this atom and 1R for this. So in total there are 4R. So we get atomic radius is equal to square root 3 by 4A, and A is the cube edge in terms of the atomic radius, that is 4R by square root 3. So now we also know what is the volume of unit cell, that is equal to A cube, and in terms of R, if we calculate, it values comes out to be 64 R cube upon 3 root 3. And if we know about how many number of atoms in the BCC, there are 2 atoms. So we have to calculate the volume then for 2 atoms or 2 spheres. So it comes out to be 2 into 4 by 3 pi r cube. And when we take the ratio of these two, the volume of 2 sphere upon the volume of unit cells, we get atomic packing factor as 68% for the BCC. So now here is the atomic packing factor for FCC. So we know that in case of FCC, atoms are present at the phases as well as atoms are also present at the corners. So in this case, we see, we find this length along the face, and we know what is the value of this, because in this case if we want to find this value, we will take this triangle. So this is the right angle triangle, and this is the perpendicular and the base. So we will calculate the hypotenuse then. So its values comes out to be square root 2a using this triangle. So 4r is then equal to square root 2a, because 2r for this phase, this atom, and 1r and 1r for this a and c atoms. So the a, that is the cube edge, comes out to be equal to 4 by root 2 r. So the volume of cube, we know that is equal to a cube. So in terms of r, you can calculate the volume of cube. So how many number of atoms are there in the FCC? 4. So if we have calculated, yes, if we have calculated the value of volume of the atoms in the unit cell, so if we calculate by one atom, that is 4 by 3 pi r cube, and we have to multiply it by 4 then. So we will divide it by the total volume of the cube, total volume of the unit cell. So we will get the atomic factor 74% in case of FCC.